Now today we would be looking at a very important concept, okay, and this is very important, the concept of resistivity. So the concept of resistivity and the formula for resistivity, that is what we would be deriving. There are a few other concepts which we will use today, and we'll recap those concepts. They have already been discussed on this channel, so definitely visit those videos. The first concept that we would be using today is that of the drift velocity, and we denote the drift velocity by a symbol Vd. And what does the drift velocity actually mean? Drift velocity is the average velocity of the charge carriers, on the net velocity of the charge carriers due to the electric field. Now that velocity is known as drift velocity. The second concept that we would be using today is the concept of relaxation time, and this is denoted by a symbol known as tau. Now what is relaxation time? Relaxation time is the average time between two collisions of the charge carriers. Okay, so these are the two concepts that we would be using, and this is the diagram that we would base our derivation on. So this diagram is again very important. It is very simple. We have applied a voltage difference, a potential of V, to a conductor whose cross section is A and whose length is L, and due to this potential difference, this potential of V, will get a current I naturally, and this is the direction of the conventional current from positive to the negative terminal of the battery. Now this current I is produced because of an electric field E which is produced inside the conductor. This electric field E would produce a drift velocity. Now since our charge carriers are electrons, they are negatively charged, so our drift velocity would be in direction opposite to that of the electric field. Okay, so that is the whole setup right here. Now what is the formulas that we will be using? So first formula that we will be using is the formula for current density in terms of the number of charge carriers per unit volume, that is N charge carrier density. E is the charge on each carrier, and we multiply it with Vd. Okay, so that is our current density. Now what is current density? We'll define it right here for that we are thorough. So this cross section area A, a current I is flowing through this entire cross section area A. Now if I divide this I by A, I get current per unit cross section area, and this is known as the current density J. Okay, current density J, this is the definition. Okay, so now we will just write it like this. J is nothing but I by A, that is by definition. Okay, nothing complicated. By definition, that is what we would it would come out to be. The second formula that we would be using today is that of Vd in terms of electric field. Now electric field and Vd, the relation between them we have again derived in a separate class, and that is again very simple. E is the electric field, this is E is the charge, m is the mass of the electron, and then multiplied by the relaxation time tau, that is the Vd. Now we substitute the Vd from this equation into this equation. What do we get? This E square will become E square, N will come right here, M will come here. Okay, and then tau will also come. Of course, we cannot forget our relaxation time, very important. Hopefully I haven't forgotten anything. And then of course there will be our electric field E. Okay, but I am not writing the electric field E right now because I want to do something with it. Now can we relate this electric field E and the voltage, the potential difference V? Now in the case of metal conductors, there is definitely a relation here, and the relation is V is nothing but E electric field is nothing but V by L. V and then divided by the length of the conductor. The voltage difference across the conductor gives us the electric field. Now this holds only for the metallic conductors. So let us just put them here. Let us just replace this. So we get here. Now our Ohm's law is something that we want to derive right here using all of these techniques. So that is the ultimate objective. So for Ohm's law, what we need is V by I. Now that is the relation, right? That is the Ohm's law. We want V by I. So for that, we just bring V and I together on one side, and we take everything else on the other side. Tau, and then this of course area will be there, which is here. Okay, now this is nothing but R, resistance, right? We know that for conductors the resistance remains constant. R is constant, it does not change. It changes only with temperature, but otherwise it is constant. That's what we say. And therefore this Ohm's law, this is the relation, right, that the ratio of V and I is constant, and that is equal to R. That is Ohm's law. Okay, that R is a constant here, and this is given in ohms. So now this R we take out separately and we write it like this. Okay, so this R we can write is M divided by E squared n tau. Okay, and then this L by A we take out separate, and this quantity M divided by E square n tau is known as resistivity. Okay, and we denote it by symbol rho. It's a Greek symbol and its units are ohm meter. Okay, that is the unit of this resistivity, ohm meter. Okay, so now we can write that our R is equal to rho L by A, where this resistivity is actually constant. It changes only with temperature and of course the material. So it depends only upon the material and the temperature, and this is known as resistivity, rho. Okay, ohm meter is the unit. Okay, that is the definition. Okay, so now from this resistivity formula, therefore we can write something. Can we find out a little more about this? So this rho is actually E square n tau. So more or less the resistivity, see, this is constant, this E square is constant, mass of the electron won't really change. More or less the resistivity depends upon only the density of charge carriers, which is n, and the relaxation time tau. Okay, that is what essentially that's what it comes out to be. Now as we increase the temperature of a conductor, for example a metallic conductor, as we increase this temperature, the electrons will move more fervently, they'll move faster and faster, and therefore they will collide more frequently. Therefore this tau will actually decrease and this rho would actually increase as I increase the temperature. Okay, so therefore the resistance of the conductors, it increases with temperature. So we can see everything from this formula. Now what about semiconductors? In the case of semiconductors, what happens? This N actually increases with temperature. The number of charge carriers itself increases in the case of semiconductors. There will be more holes, there will be more electrons in the semiconductors in the conduction band as I increase the temperature. Because of this increase in N, in the case of semiconductor, the rho actually decreases, or resistance of the semiconductor, the resistivity and in turn the resistance of the semiconductor actually decreases with increasing temperature. So many things we have just found out from this formula for resistivity. Now the temperature dependence of the resistivity is actually given by this formula. The rho is dependent on temperature. This rho 0 is the initial resistivity at temperature T0, and 1 plus alpha T minus T0. So T0 is the initial temperature, T is the final temperature. And notice that this formula, this linearity of the resistivity, okay, so this is a linear formula for resistivity. It depends, it only holds as long as this T is nearby T0. So this is my T0. As long as I am in this range, my T lies nearby this T0. Okay, this formula would actually hold. Alpha is a proportionality constant. It is known as the temperature coefficient of resistivity. Okay, so hopefully things are very clear. The concept of resistivity is completely set in your minds with this class. Numericals are asked all the time. Okay, so numericals are asked when we talk about this current density and this electric field. Okay, the relationship between the current density and electric field, which is given right here. Okay, so this is our electric field E and this is our current density J. So current density J is related to electric field using this formula right there. Okay, and that is very important. It is very important for numericals. Okay, questions are asked all the time based on this. Okay, so thank you very much.